Hi everyone, I'm Zohreh and I hope you're doing great. In last video, I talked about first chapter of Holliday Physics book. I explain base quantities and units, the unit system, scientific notation, chain link conversion, significant figures and decimal places. In this video, I'm gonna teach you second chapter of Holliday Physics book, which is about motion along a straight line. I will talk about position and displacement, average velocity and average speed, instantaneous velocity and speed, acceleration, constant acceleration, free fall acceleration, graphical integration in motion analysis. If you are interested in physics, then you can join and enjoy.
Welcome to our Physics Holiday Book Adventure. Today we'll explore the fascinating world of motion. Our purpose of physics is to study the motion of objects, how fast they move, for example, and how far they move in a given amount of time. In this chapter, we study the basic physics of motion where the object moves along a single axis. Such motion is called one-dimensional motion. The classification and comparison of motions called kinematics. Some general properties of motion is restricted in three ways. The motion is along a straight line only. The line may be vertical or horizontal or slanted, but it must be straight. Second, forces, pushes, and pulls cause motion but will not be discussed. In this chapter, we discuss only the motion itself and changes in the motion. The moving object is either a particle, by which we mean a point-like object such as an electron, or an object that moves like a particle, such that every portion moves in the same direction and at the same rate. Position and displacement. To locate an object means to find its position relative to some reference point, often the origin or zero point of an axis, such as the x-axis in figure 2.1. The positive direction of the axis is in the direction of increasing numbers or coordinates, which is to the right in figure 2.1. The opposite is the negative direction. A change from position x1 to position x2 is called a displacement x, where delta x is equal x2 minus x1. The symbol delta, the Greek uppercase delta, represents a change in quantity, and it means the final value of that quantity minus the initial value. A displacement in the positive direction always comes out positive, and a displacement in the opposite direction always comes out negative. For example, if the particle moves from x1 is equal 5 to x2 is equal 12, then the displacement is delta x 12 minus 5 is equal 7. The positive result indicates that the motion is in the positive direction. If instead the particle moves from x1 is equal 5 to x2 is equal 1, then delta x will be equal 1 minus 5, which is minus 4. The negative result indicates that the motion is in the negative direction. Note that the displacement involves only the original and final position. For example, if the particle moves from x equal 5 out to x equal 200 and then back to x equal 5, the displacement from start to finish is x equal 5 minus 5, which is 0. Displacement is a vector quantity, which is a quantity that has both a direction and a magnitude. Average velocity. Average velocity, V average, which is the ratio of the displacement delta x that occurs during a particular time interval delta t to that interval. V average is equal delta x over delta t is equal x2 minus x1 over t2 minus t1. A common unit for V average is meter per second. You may see other units in the problems, but they are always in the form of length over time. On a graph of x versus t, V average is the slope of the straight line that connects two particular points on the xt curve. As you can see in the figure, 1 is the point that corresponds to x2 and t2, and the other is the point that corresponds to x1 and t1. Like displacement, V average has both magnitude and direction. It is another vector quantity. The average velocity, V average, always has the same sign as the displacement x because t is always positive. Average speed. S average is a different way of describing how fast a particle moves. Whereas the average velocity involves the particle's displacement, delta x, the average speed involves the total distance covered. For example, the number of meters moved, independent of direction. That is, S average is equal total distance over delta t. Because average speed does not include direction, it lacks any algebraic sign. Instantaneous velocity and speed. The velocity at any instant is obtained from the average velocity by shrinking the time interval delta t closer and closer to zero. The average velocity approaches a limiting value, which is the velocity at that instant. V is equal delta x over delta t is equal dx over dt. Note that v is the rate at which position x is changing with time at a given instant. That is, v is the derivative of x with respect to t. Also note that v at any instant is the slope of the position time curve at the point representing that instant. Velocity is another vector quantity and thus has an associated direction. Speed is the magnitude of velocity. A velocity of minus 5 meter over second and one of plus 5 meter over second both have an associated speed of 5 meter over second. Because, as I mentioned, speed is the magnitude of velocity. Acceleration. When a particle's velocity changes, the particle is said to undergo acceleration or to accelerate. For motion along an axis, the average acceleration A average over a time interval delta t is A average equal delta v over delta t is equal v2 minus v1 over t2 minus t1. The instantaneous acceleration, or simply acceleration, is A is equal dv over dt. Graphically, the acceleration at any point is the slope of curve of bt at that point. We can combine previous equations. A is equal dv over dt. Here we can put dx over dt instead of v, and then we will have d squared x over dt squared. In words, the acceleration of a particle at any instant is the second derivative of its position xt with respect to time. A common unit of acceleration is the meter per second squared. Acceleration is another vector quantity, has both magnitude and direction. Here is the proper way to interpret the signs. Note that if the sign of the velocity and acceleration of a particle are the same, the speed of the particle increases. But if the signs are opposite, the speed decreases. It is really important and useful point. Constant acceleration, a special case. A is equal A average is equal delta V over delta t equal V minus V0 over t minus 0. Here V0 is the velocity at time t equal 0 and V is the velocity at any later time t. We can recast this equation as V is equal V0 plus AT. Take the derivative of this equation yields A is equal dV over dt, which is the definition of A. We also can write V average is equal x minus x0 over t minus 0. And then, as x is equal x0 plus V average t, in which x0 is the position of the particle at t equals 0 and V average is the average velocity between t equals 0 and a later time t. The average velocity over any time interval, for example from t is equal 0 to a later time t, is the average of the velocity at the beginning of the interval v0 and the velocity at the end of the interval v. For the interval from t is equal 0 to the later time t, then the average velocity is v average is equal 1/2 v0 plus v. Here we have some derivation. Substituting the right side of equation v is equal v0 plus at for v yields after a little arrangement 2v average minus v0 is equal v0 plus at, and then 2v average is equal 2v0 plus at, and v average is equal 1/2 at plus v0. Finally, substituting above equation into x is equal x0 plus v average t yields x minus x0 is equal 1/2 at squared plus v0 t. Quotient v is equal v0 plus at and x minus x0 is equal 1/2 AT squared plus V0t are the basic equations for constant acceleration. These two equations can also be combined in three ways to yield three additional equations. V squared is equal V0 squared plus 2a x minus x0 is the first one. Second is x minus x0 is equal 1 half v plus v0 times t. And the third one is x minus x0 is equal vt minus 1 half at squared. First, we can eliminate t to obtain equation v squared is equal v0 squared plus 2a x minus x0. And how? We have equation v is equal v0 plus at. Then we square the both sides. We will have v squared is equal v0 squared plus a squared times t squared plus 2v0at. The both part, we can put a out of parentheses and we will have a times at squared plus 2v0t. And that we also put 2 out of parentheses and we will have 2a times 1 half at squared plus v0t. As we can see before, 1 half at squared plus v0t is equal x minus x0. And then we have what we want. V squared is equal v0 squared plus 2a x minus x0. This equation is useful if we do not know t and are not required to find it. Second, we can eliminate the acceleration a between equations to produce an equation in which a does not appear. The equation is x minus x0 is equal 1 half v plus v0t. And how we obtain this? We start from v is equal v0 plus at. A is equal v minus v0 over t, and then we put a in the equation x minus x0 is equal 1 half at squared plus v0t, and we have x minus x0 is equal 1 half. We put v minus v0 over t instead of a times t squared plus v0t. And then we calculate that and cancel the t in denominator. We will have x minus x0 is equal 1 half v minus v0t plus v0t. And finally, x minus x0 is equal 1 half v plus v0t. And for the third equation, finally we can eliminate v0, obtaining equation x minus x0 is equal vt minus 1 half at squared. And how we obtain this? We start from v is equal v0 plus at. We obtain v0 from this equation. v0 is equal v minus at, and then we put this equation for v0 in the equation x minus x0 is equal 1 half at squared plus v0t. And we will have x minus x0 is equal 1 half at squared plus v minus at, which is the definition of v0 times t. And we will have x minus x0 is equal vt minus 1 half at squared. look at constant acceleration. Equations v is equal v0 plus at and x minus x0 is equal 1 half at squared plus v0t are the basic equations from which the others are derived. Those two can be obtained by integration of the acceleration with the condition that a is constant. To find it, we rewrite the definition of acceleration as dv is equal a dt. We next write indefinite integral or antiderivative of both sides. Integral of dv is equal integral a dt. Since acceleration a is a constant, it can be taken outside the integration. We obtain integral of dv is equal a integral of dt, and then we will have v is equal at plus c. To evaluate the constant of integration c, we let t is equal 0, at which time v is equal v0. v0 is a times 0 plus c equals c, and finally v is equal v0 plus at. To derive equation x minus x0 is equal 1 half at squared plus v0t, we rewrite the definition of velocity as dx is equal v dt. And then take the indefinite integral of both sides to obtain integral of dx is equal integral of v dt. Next, we substitute for v, we beat v is equal v0 plus at. Integral of dx is equal integral of v0 plus at times dt. Since v0 is a constant, as is the acceleration a, this can be rewrite as integral of dx is equal v0 integral of dt plus a integral of t dt. Integration now yields x is equal v0t plus 1 half a t squared plus c, where c is another constant of integration. At time t equals 0, we have x is equal x0. X is equal v0 times 0 plus 1 half a 0 squared plus c. And finally, x is equal v0t plus 1 half at squared plus x0. Free fall acceleration. If you toss an object either up or down and could somehow eliminate the effects of air on its flight, you would find that the object accelerates downward at a certain constant rate. That rate is called the free fall acceleration, and its magnitude is represented by g. The acceleration is independent of the object's characteristics such as mass, density, or shape. It is the same for all objects. The equations of motion for constant acceleration also apply to free fall near Earth's surface. That is, they apply to an object in vertical flight either up or down, when the effect of the air can be neglected. However, note that for free fall, the direction of motion are now along a vertical y-axis instead of the x-axis, with the positive direction of y upward, and the free fall acceleration is negative. That is a downward on the y-axis toward Earth's center, and so it has the value minus g in the equations. The value of g is equal 9.8 meter over second square. Graphical integration in motion analysis. Integrating acceleration when we have a graph of an object's acceleration a versus time t, we can integrate on the graph to find the velocity at any given time. Because a is defined as a is equal dv over dt, the fundamental theorem of calculus tells us that v1 minus v0 is equal integral of t0 to t1 a dt. The definite integral can be evaluated from an AT graph. How? Because integral of t0 over t1 a dt is equal the area between acceleration curve and time axis from t0 to t1. Note that when the acceleration curve is above the time axis, the area is positive, and when the curve is below the time axis, the area is negative. Integrating velocity. Similarly, because velocity v is defined in terms of the position x as v is equal dx over dt, then x1 minus x0 is equal integral of t0 to t1 v dt. The definite integral can be evaluated from a VT graph. And how? Integral of t0 to t1 v dt is equal area between velocity curve and time axis from t0 to t1. And you can see in the graph. And that concludes our journey through the world of motion. Remember, understanding and mastering this subject is essential for any aspiring physicist. Stay curious and keep exploring.